Hey everyone, welcome back to the channel. In today's video, we are diving into how to make your Expo applications faster. We'll be going through some of the best practices shared by Evan Bacon himself in the official Expo blog. And I'll walk you through practical visual examples of how these things actually affect your application. We'll talk about the difference between JavaScript thread and the UI thread, how to debug performance issues, and how the new React compiler can fix unnecessary re-renders automatically. And finally, we'll go one step further into multi-threading JavaScript with React Native Worklets. This one's really cool. Let's dive in. Before we dive into the examples, let's quickly highlight a few of the best practices from Evan's post. And by the way, something very important to keep in mind is that fast applications and good performance go hand in hand by writing good code and following best practices. So definitely, you should follow all the steps listed here. First of all, of course, use TypeScript. At this point, I think everyone is using TypeScript, and if you are not, you need to prioritize that. Use static JavaScript features. I think this goes into the just following best practices step, which means avoid using var, instead just use const as much as possible and let. Also import and export instead of require, although required is okay for assets like images. Enable slint and static analysis. This helps catch bad patterns early. Use the React compiler. We're going to see some examples here, so I don't want to get ahead of myself, but just so you know, the React compiler is enabled by default on SDK 54 and above. So if you're using an older SDK version, make sure that you have it enabled because it really helps with performance. And we're going to learn more in a moment. Also, in case you're using an older SDK version, just refer to this amazing blog post with instructions on how to enable it. So if this is actually possible for you, if you are already using React 19, like I said before, it's just a matter of using the latest APIs available, like use, instead of having a custom hook when you are exporting a context, for example. You can just pass the context directly now. Here we have an example of how this looks like. Just pass the context directly, access the value, and boom. This also helps the React compiler optimize better your code. All right, before we dive in, actually one more thing that I wanted to mention is that it's very important that you test on a real device, especially if you're having performance issues. That is because the simulator runs on your computer's hardware, meaning that it doesn't really reflect real-world performance. So use a real device to test performance issues. In case you didn't know, React applications actually run on multiple threads. This is crucial to understand so that you can write good React Native code and you avoid blocking the JavaScript thread. You can think of these threads like workers, each doing a specific job. The first one is the JavaScript thread. You can see it here in yellow. This is where your React code lives. Your logic, your state updates, API calls, everything. But something very important is that the JavaScript thread doesn't draw anything on the UI. The JavaScript thread only decides what should be shown and then sends that information over to another thread. That's where the UI thread comes in, and you can see it here in blue. So the UI thread is also known as the main thread, but honestly, personally, I kind of find that a bit confusing. So from now on, let's just call it the UI thread. So the UI thread handles everything you see, like rendering views, handling touches, views, running animations, basically all the visuals. And this is like the happy path of how these two threads work together. So first of all, we have this event, right? Like render the application that we are sending to the UI thread. At the beginning, everything was idle, so you don't see anything on screen. But after the UI thread receives this event, it's going to repaint the UI or refresh the UI, and then we have our little counter application, right? It's starting at 6, it's fine. In this case, let's say that the user pressed the count button, right? So we're going to get this on press, and on the JavaScript side, you can imagine that we're going to set use state using React. We're going to call a function, maybe create an API request, whatever. And basically it's just calling a function, right? After we finish processing that, we updated the state, we can go back to the UI thread and ask it to refresh. So the user is going to see now the count being 7. Of course, this is going to happen most of the time instantly because all these operations are non-blocking. So in short, the JavaScript thread decides what should happen and the UI thread actually makes it happen on screen. Now, this is super important when it comes to performance because if you block the JS thread, maybe with some heavy computation, your whole app is going to freeze. Let me show you an example of how blocking the JavaScript thread would look like. So here I have this thread demo component, and on the right, we are just rendering some text. As you can see here, just simple text. And then we have a button that is calling block the JS thread function. And if we take a look at this function, I actually took this snippet from Evan's post, and it's just basically going to block the JavaScript thread entirely because we have a while loop that is going to be running for 3 seconds. Okay, doing this calculation, just math random for 3 seconds nonstop. So we're going to be blocked in this line 14 for 3 seconds, meaning that the JS thread is not going to be able to send updates to the UI thread. And yeah, after 3 seconds, we're finally going to set the count. But let's see what happens if I go ahead and block the JS thread. Notice that the press count is 0. So let's press this button. 1, 2, 3, and after 3 seconds, we get the update. But also notice that I have a CSS animation using React Native Reanimated. And Reanimated actually uses the UI thread to handle all the heavy stuff and animations. So that's why even though my application is frozen on the JS thread, the UI thread and the animation keeps running smoothly. And this is how the animation looks like. It's just a very simple animation, nothing to do with everything else. So in this first example, of course, it's a good idea to just, don't do heavy computations here. If I just comment this while loop, then go back and press this button, now everything works smoothly because these operations like setting state, setting some variables are just non-blocking operations, and JavaScript can handle those events super quickly, send that to the UI thread. The UI thread is super fast, updates the UI, and we have a responsive UI. But let's understand threads and let's talk about finding performance bottlenecks because it could be not obvious like this one, right? It could be that you have maybe a super big component and it's hard to spot where the bottleneck is. So let's see how you can find these issues. Let me show you a different example that I have here called render example. So this is my component expensive child. And then we have this render component, just has 2 state variables, 2 buttons, and a text, and the expensive child, which has a count. So let's see that we haven't checked the expensive child and we are just trying to increase the counter. If I press the button, you notice that it takes a while and then updates. So if I press it twice, actually, it's going to get stuck, and it's actually going to detect the press events that I'm doing, but it's going to update after the time that is taken to process this child in the JavaScript thread. Now, what I want you to see in this component is that we have this text, right, that we are rendering here with this button. This is just setting the text to a random string and just displaying it here. But notice what happens if I press this change text. It also takes like 2 seconds, and then we see the change, the new text update. This is very slow, it feels super laggy. So the way you could start identifying these issues is by using the DevTools. If you open your terminal in VS Code, you'll notice that we have this Open Debugger option by pressing J in the terminal. So let's do that. Press J, and this will bring up the DevTools. So in the DevTools, you can access the console to see what's happening with the logs in your application. Once you are in the DevTools, you can also press Command R to refresh the application and start from 0. And there we go. So everything is working. It means that it's connected if it's refreshing. But what I want to spot here is what's happening in this component. So if I go to the profiler and I press on this little gear icon, make sure that you have this highlight updates when components render. This will help you know which components are being re-rendered as you interact with the application. So let's enable this. Let's close that. And then you can also find, by the way, more information about the components in the Components tab. You can press this icon, mouse pointer, and then just go to your application and click on the component that you want to inspect. So in this case, I press the increment count. This will take me to the information. This will show me the information of the component. And also, very importantly, who is rendering this component. So I can see that this is coming from the render example component inside the index.tsx screen. But anyways, once you enabled highlight updates when components render, you can go back to the application and, for example, let's press increment count. As soon as I press the button, you notice that it highlights with a rectangle that is letting me know that the component re-render. And as soon as we finish computing the expensive child, you notice that actually everything is re-rendering, including the text, the change text, and the text, even though we are not updating this variable. So let's do it again. I'm going to press it again. You see that we have the highlights there. But most importantly, this could be totally fine, right? Because we have this expensive child. But something that really worries me is that if I change the text, which has nothing to do with the counter, the application still gets stuck, and after a moment, it re-renders everything. So this is very bad. The way you can actually fix this is by memoizing some of the components and preventing re-render. But you can actually, still keep this ugly code and bad code that is blocking the JS thread and have it perform well just by enabling the React compiler. So I said this before, starting from Expo SDK54, the React compiler is enabled by default, but if you really want to, you can disable it in the app.json file. This project that I'm showing you, it's using SDK54, and if you set under experiments, React compiler equal to false, this is going to disable it. So we can actually just remove this and it's going to be enabled by default, or just set this variable equal to true and save it. All right, so once I make this change, I'm going to restart my server. So let's clear the terminal and let's run npx expo start. And I'm going to pass the clear flag to make sure that we don't have any cache and we are using the compiler correctly. All right, so now the server is running. Let's go back to the application. And I'm going to completely quit Expo Go in this case, open it again to make sure that the bundle loads without cache. Okay, let's select my app. And now let's reconnect the DevTools by pressing the reconnect DevTools. Yeah, so in this case didn't work. So I'm going to just close and open it again. Let's go back, press J. Okay, so the debugger is open again. Let's press Command R just to make sure that everything is connected. And, again, just make sure that we have the highlights in the profiler. It's already enabled, so I don't have to worry about it. And let's try to test the application after enabling the compiler. Let's increase the count. This component still expensive, but if you notice now, we didn't do anything, just enable the compiler. And now each time that I compute the increment count, it only re-renders the child or the component that it actually changed. And most importantly, when I change the text, this is instantly fast. Even I can spam this and it's going to update right away, because at this point it's not recomputing the expensive child. Now, if for some reason you are not able to use the React compiler, you can manually use memo and use callback to cache functions and components. Also, if you are still working in adopting the React compiler, let me stop the terminal. You can run a health check to see if you can adopt the React compiler by running npx react compiler health check add latest. This is actually a package that is going to just run a quick check on your project, and it's going to let you know if it's okay or if it's in a good state to adopt the React compiler. This is one thing you can do. And then there is an extension that you can use in VS Code. It's called React Compiler Marker. As you notice, I already have it enabled. And this extension is going to let you know if the component is optimized for the React compiler or not. And if you pay attention, this is letting me know here that my component can be optimized by the React compiler. This is a nice extension to have because it's going to let you know if you are doing something wrong right away and you can fix it and enjoy all the React compiler benefits. Now let's talk about something that's even more powerful, multi-threading JavaScript. All right, so up to this point, we were able to enable just the React compiler and now our application is slightly faster, but we are still computing this expensive child. And if we go back to the application, when I press the increment count, you can see that the first press event registers correctly. But what happens if the user, notices that the application is getting slow, so it presses again the same button, thinking that it didn't register the first time? So I'm going to press it, let's say 4 times. 1, 2, 3, 4. We get the animation the first time that we press the button, and then it feels very slow. We don't see the value update until it finishes processing all the tasks that were blocking the JS thread. And finally, we get the update. So what's happening in the application is that when you press the button for the first time, the user presses the button, we're instantly going to start processing the press on the JavaScript thread, meaning that we are completely blocking the JS thread for, in this case, 3 seconds. And if the user keeps spamming the same button 3 more times, you notice that the UI can still register and get these events because the UI thread is not blocked and it's detecting that the user is pressing the screen and it's sending those events to the JS thread. But at this point in time, the JS thread is completely blocked, still processing the first press. So what's happening is that the JavaScript thread is going to start queuing these events and then process them once the JavaScript thread becomes idle again. So once it finished processing the first press, you'll notice that it's going to request a UI render, and then right away it's going to start processing press 2, right away it's going to start processing press 3, right away it's going to start processing press 4, and finally, after all this time, which is going to be 12 seconds later, we will get finally a UI refresh. This is very bad because all this time that we are blocking the JS thread, we are not able to send updates to the UI nor receive updates. We could receive updates from the UI thread, but we cannot react in the JavaScript thread. And by the way, if you are wondering why the first time that I press the increase counter, let me press it 4 times. 1, 2, 3, 4. We get 1, and then it's going to jump all the way till the end, the final calculation. That is because of the way React batches updates. First of all, we handle the first event correctly, and then we request a UI render. But then after that, because we have 4 events queued already, 3 events queued, we are going to start processing those before React gets a chance to re-render the component. So although the value in the counter is increasing, we are not able to repaint the UI until we finish processing all these queued tasks. So if we go back to the code, the solution would be just don't block the JS thread, right? But let's say that you need to do a heavy computation, your application requires it. Normally JavaScript runs on a single thread, we already know that, but libraries like React Native Worklets can create new runtimes and offload heavy computations to a separate thread, keeping your app responsive. Let's see it in action. This example is using a very powerful feature from React Native Worklets. We still have this heavy computation, which is completely blocking for 3 seconds. But thanks to React Native Worklets, we can create a different runtime to offload this operation. So from React Native Worklets, I'm importing create worklet runtime and the function run on runtime. So the create worklet runtime allows you to create a runtime, and you can think of this similar to the web. On the web, we have workers that can allow you to do multi-threading processing in the background. So in React Native, we have worklets. First of all, we can start by defining a new runtime. So in this case, I'm naming mine worker, but you can name it as you want. And then this takes, apart from the name, an initializer function, and this is just printing that the worker runtime was initialized. Then this worker runtime is being used here when we run the heavy computation. When we run the heavy computation, we can call run on runtime function. This will take the runtime, which is my worker runtime, and the function that is going to handle the heavy computation. Now, in order for React Native Worklets to know that this code needs to be sent to another runtime, we need to use this directive worklet. So everything inside this function is going to run on the worklet, effectively offloading this process from the JS thread, keeping our application responsive. So when I increase the count, that means that I can keep using my application, increasing the counter, and run the heavy task at the same time. So let's see it in action. I'm going to press increment. My application is very responsive, non-blocking task up to this point. But if I run the heavy task, I can still use the counter. And if I open the console, we get the log. It says heavy task done on the UI worker thread. Now I have another example that is, I think, more illustrative. It's using the Fibonacci sequence to create the heavy computation. This is a bit more complex. We have a bunch of state variables because there is a lot going on here. We have the JS counter, and on top of that, we can compute something heavy, like Fibonacci of 38 is going to take like 5 seconds. If we do it in a naive way, of course, which is what we want in this case. So here we're doing the same. We create a worker runtime, and the name is fifth worker in this case. And then we can just run the heavy computation, which is calculating Fibonacci, passing the Fibonacci that we want to calculate. So let's say that I press 38. This is going to be 38. And then you can also pass this handle result function, which is just setting the value calculated on the different thread using useState so that we can display it in the UI. So when we call run Fibonacci, we can just pass the number of the sequence that we want to achieve. So 38, 40, or 42, just like that. And then this is just going to start these state variables. Once we get the result, we can display it by setting the state with this function. So let's calculate Fibonacci of 38. You can see that it says computing, and at the same time, I can keep using the counter. Once it finishes completing, we get the final result on screen coming from the different thread. This is huge because my JS thread stays free while we can do heavy computations like fib of 40, which is going to take a while. So let me explain what is actually happening in this case. So what we are doing at this point is introducing a new runtime, or you can think of it as a new thread. I'm adding this worklet thread here, which is going to calculate Fibonacci of 38. So as soon as the user presses this button, we're going to get that event in the JS thread. The first thing that we do is offload that processing to the worklet thread. So this process is going to actually block the worklet thread. But the good thing about this is that the JS thread can still keep processing regular non-blocking tasks, like increasing the counter. And we can still communicate with the UI thread and receive events from the UI thread, react to the counter, do stuff, normal tasks. And after the worklet finishes the processing, we get the result in the JS thread, we set the state, and finally we let them know the UI thread that we can render the result. The big difference here is that although it took the same time, it was a heavy computation, the application remained responsive. This is a game changer for things like real-time data, math-heavy logic, of course, or even image processing. So even if your app is doing something heavy, your users don't feel it. And that's it. Now you know how to spot performance issues, understand what's happening under the hood, and even use multi-threading in your Expo apps. Huge thanks to Evan Bacon for the amazing blog post, and I'm going to leave it in the description so you can check it out. I'm also linked the documentation to the React Native worklets in case you are curious and want to learn more. And if you find this video helpful, give it a like and subscribe for more deep dives like this one. I'm Beto, and I'll see you in the next one.